Okay, let's talk about systems of differential equations and how to study them. But today we're just going to I'm going to tell you what these things look like and the sort of things they can be used to model and represent. And we'll only get into the real solution of these things at the very end of this presentation. And I'm only going to touch on it, and we'll really discuss how to solve these things in earnest in the next videos. So right now, just sit back and you want to try to understand how these things are corresponding to physical systems. Just you want to understand what these represent, these systems of equations in differential equations. Begin with our first example, a predator-prey model, where you imagine you have predators and prey living together, possibly in harmony, we hope, in some kind of environment, and we measure the prey population is a function of time, and the predator population is also a function of time. So we refer to these two populations as x of t and y of t, and they satisfy these differential equations. Where did I get these differential equations from? Well, first of all, they're standard in biology. They're the first thing that an environmental biologist studies, or at least if you're a mathematical biologist. It's the simplest kind of equation that can possibly reasonably model predator-prey interaction. So what's happening here? First, I want you to imagine, for the moment, imagine we had no predators. So imagine that y were 0. Then this is gone, and we just have prey growing exponentially. X prime equals alpha x means exponential growth of your prey population x. But now we say, well, suppose the predator population is not 0. Suppose it were something bigger than 0. Then you got to figure what's going to happen is the predators will eat some of the prey. That's what predators do. And I figure somebody realized, I suppose, that the amount of eating that's happening, it makes sense to say that it would be proportional to x times y. The reasoning behind that is the more predators you have and the more prey you have, the more they're going to interact. So x times y measures the interaction. It's a simplistic model, but it's also reasonable. So we're going to say that prey in the absence of predators would grow exponentially, but they also die proportionally to the amount that they're interacting with predators. So that's what this first equation says. On the other hand, predators, who are modeled by y, they flourish when they are eating a lot of prey. So they flourish proportionally to how much they're interacting with prey, proportionally to x times y. On the other hand, what predators don't like are other predators. If there are too many predators, then there's competition for food. When there's competition for food, predators starve. Now, the more predators there are, the more competition there is. So the amount of dying that the predators are doing can be said to be proportional to the number of predators. So predators flourish proportional to the amount they're eating, and die proportional to the number of predators there are due to competition. With these two equations, we can visualize solutions. We can draw what's called a phase plane, and we can find what are called equilibrium solutions. And we're going to use these values of the constants alpha, beta, delta, and gamma. So now they are fixed numbers as given here. And we're going to assume that x of t and y of t measure populations in thousands, so that it'll make more sense to have decimal answers for things. So, what is an equilibrium solution? Well, think about it physically, or biologically, if you will. An equilibrium solution, well, what would it mean for the predators and preys to be in equilibrium? So that meaning their populations are roughly stagnant, not changing. Well, that would imply that if something's not changing, if something's constant, then that means its derivative is 0. So by setting these derivatives equal to 0, that tells us when the predators and prey will reach equilibrium. So I've gone ahead and did that. I set these derivatives equal to 0. And then solving for x and y with the given constants of alpha, beta, delta, and gamma, I solved the equations and got 0, 0, and 3.25, 0.3 repeating. These are equilibria. This equilibrium means both populations are extinct. That's clearly equilibrium. Neither population would be changing if they were both extinct. On the other hand, there's one other fascinating equilibrium point. It's here when we have 3,250 prey and 333 predators. And so those are called equilibrium points. And if you try not to think about them too abstractly, they really are just if this is x and this is y, and you plug those in to these equations, you get 0 equals 0 and 0 equals 0. And they're extremely important points. They're the only points where we can have constant solutions. By definition, because if you chose any other point besides these and plugged them in to the differential equation, you'd get some non-zero number on the right-hand side, meaning x prime and y prime are non-zero. But if x prime or y prime are not 0, then they're not constant. If they're not constant, then they're changing. And if they're changing, then they're not equilibria. So these are the only equilibria for our system. Extinct and this, whatever this is. Now that we've found equilibria, let's discuss what other non-equilibrium solutions might look like. A solution can be visualized by a parametric plot because, as you can see, if prey population depends on time and predator population depends on time, then you can plot the predator and you can plot the prey and predator populations as a parametric plot depending on time. So for example, we can find a solution starting at the point 3.3, 0.3. And that's not an equilibrium point. It's close, but it's not an equilibrium point. And here's that point. I put it right here in black. And then I defined my differential equations, and I used ND-solve to solve those differential equations for the variables x and y as functions of time. And then I did a parametric plot of my solutions on my given window and labeled the axes prey and predator so that you see what's happening. So the population started here at 3,300, 300. 3,300 prey, 300 predators. What happened was because there were relatively fewer predators than equilibrium, the prey were flourishing. The prey were flourishing because they weren't getting eaten quite so much, with the predator population being small. So they flourished for a while, but then what happened was, because the prey were doing so well, the predators started to have more to eat. And when the predators have more to eat, their population increases for a while. But then when the predator population increases enough, then the prey are quite unhappy because they're getting eaten more. And they die more. Things usually die when they get eaten, and so their population decreases. So now there are less prey. But then when there are less prey, the predators have less to eat. And so when the predators have less to eat, they starve, and so their population decreases as well. And finally, when the predator population decreases, there are less things eating the prey, and so the prey are happy and they flourish again. And actually, this solution is periodic. You actually get back where you started. And I haven't solved this problem by hand yet, so I can't tell you how long this process takes. And in fact, I haven't even told you the units of time in this problem. I'm not even sure if we're measuring time in years or days. I'm not sure which would even make more sense for this problem. I really have no idea. So we don't know everything we'd like to know, but we do know that the circle of life is taking place quite literally here. So I created a function called generate plot from initial data. And it's a convenience function that allows us to plot these things using only one line of code instead of 5. But I actually found something online called pplane. There's a link to it on my website and in the description of this video, if I remember. So definitely Google pplane. There's a professor at Rice University, can't remember his name, but I'll definitely give him credit. But his software is available for academic use for free, easy download. It's a Java file. It's a really nice program that allows you to generate these sorts of plots without writing any code at all. It's a point-and-click interface. So really nice software here that allows you to avoid having to write all this code to study these kinds of equations. You'll see a lot more of that code in you'll see me use pplane in later presentations, but I wanted to show you how you can do this in Mathematica, because I didn't want it to be entirely mysterious to you how pplane works. This is probably very similar to how pplane works under the hood. Anyway, I plotted several solutions using different initial data. So I chose 3 different initial data points and plotted them, and then used ND-solve to solve the system of equations for the predator-prey model, and we get these loops. They're always periodic solutions. They always end up back where they started. So that's pretty interesting. And let's visualize a different problem now. I'm afraid I can't tell you what these equations represent. I don't quite know. So you can tell yourself a story about X representing, I don't know, the unemployment rate, and Y representing inflation, or if you're into economics, or perhaps you like to study neuroscience and X is the voltage on some axon and Y is something else. Who knows? But I really don't have a physical interpretation of these equations for you. I'm just going to slap them down here on the screen and we're going to study them. It turns out that I found 2 solutions to these equations for you. By the way, what do I mean when I say these are solutions? This is a vector. going to start writing vectors in column notation. So this is the vector 2, 5. And when you distribute this, when you scale by e to the minus 2t, so this is the vector 2e to the minus 2t, comma, 5e to the minus 2t. And I'm saying that if you call that first component x, and you call the second component y, and plug them in here, I claim that it's a solution. And similarly for this solution. And I'm calling these solutions bold-faced x1 and bold-faced x2. Every time I use a boldface, it means it's a vector instead of a scalar. So, finally, we're going to visualize these solutions. So, if we find a solution and refer to its first component as x and its second component as y, this is a parametric curve, as we discussed before in the predator-prey problem. And the velocity, hopefully you'll recall this from a calculus course that you've taken, but the velocity of a parametric curve is found by just taking the derivatives of the components, respectively. And on the other hand, we know that if it's we know that x prime of t is half x minus y, and we know that y prime of t is minus 5/4 x minus 3/2 y. So that means we know the velocity of this parametric curve. The velocity must equal these things for the components. So this is a visualization in terms of velocity. So I'm saying that we know what the velocity ought to be at any point, and so we can represent what the velocity ought to be with a vector, and what you have is a vector field that says what your solution's velocity have to be at any time t. So now we're going to verify algebraically that these are indeed solutions. So look at this first solution, for example. x1 of t is e to the minus 2t times the vector 2, 5. So this is the x component, and this is the y component. Plug those in for x and y here. And you get, so this is the derivative of x. This is, I plugged in x here, I plugged in y here. And that is true. If you do the arithmetic, it is definitely true. And similarly, this is also true when you plug in all the stuff for y prime, x, and y. So this is true as well. And I'm going to leave this as an exercise for you to do the same thing with x2, e to the t times the vector -2, 1. And then I also want you to check, and this is kind of important, I want you to check that if you take a constant, let me fix that, that's not what I meant. If you take a constant times the first solution, I'm going to use an arrowhead to indicate that it's the vector, not the scalar, plus another constant times the second solution, I claim that once again, if you plug anything of this form into this differential equation, it will still be satisfied. And finally, let's visualize a few of these solutions. So I took a few different linear combinations. So first of all, I defined x1 and x2 that were given in the problem, and then I defined a few different linear combinations, such as 1x1 plus 1x2. I did 1x1 plus -2x2, half x1 plus -half x2, and -1x1 plus 0.3x2. These are all linear combinations, and if you did the last problem, you've checked that they are indeed solutions, and therefore they should thread through the vector field. and they do. So, how did we find those solutions? Well, it turns out you can always find solutions of the form e to the lambda t times a vector u. So the question really is, what is lambda and what is u? Because not any values of lambda and u would have worked. In fact, those were the only values that would have worked, times a constant on u, but that's neither here nor there. We're severely restricted in what lambda and u can be. So how do we find them? Well, first of all, it helps us if we can write this this equation in what's called matrix and vector form, where instead of writing them separately, you refer to x prime comma y prime as a vector x prime, and then the right hand side is matrix times vector, where the matrix is this, just the coefficients, and the vector, of course, is x comma y. And if you're not familiar or you've forgotten about matrix multiplication, we're going to be doing an entire video on it following this. But for now, you can take my word for it that this notation means these equations, just in a more compact form. Now, we're trying to find a solution of the form e to the lambda t u. So if we plug it into this differential equation, what we get is this. When we take the derivative of this, we get lambda e to the lambda t. So we have this times u now equals e to the lambda t au. And if you divide both sides by e to the lambda t, au equals lambda u. And this is an extremely important equation. It says that the vector u is parallel to its image under the linear transformation A. And if that meant nothing to you, then it'll all make sense at the end of the next video on linear algebra, hopefully. This equation is called the characteristic equation, also called the eigenequation for the matrix A. And again, so that's the end of this video, but the next one is going to cover all the linear algebra you need to make sense of this equation so that we can solve these differential equations once and for all.